Welcome to my video course on engineering FRCMS. Today, we're zooming in on a truly brilliant piece of network engineering within the future railway mobile communication system. We're talking about implementing multipath control, specifically multi-UE control. We're going to explore exactly how we engineer a network capable of taking a single application's data stream and distributing it concurrently over multiple, separate physical connections. The ultimate goal? Ultra-high reliability. It's a massive game changer, and I honestly can't wait to unpack it for you.
So here's our quick roadmap for today's explainer. We'll start with the need for ultra-reliability, then move into defining FRMCS Multipath. From there, we'll map out the multipath architecture, get into the weeds of data flow management, and finally wrap up with cross-domain transport.
Let's kick things off with Section 1, the need for ultra-reliability.
Okay, let's dive into this. The entire push for FRMCs is really being driven by incredibly demanding, high-automation digital rail use cases. We aren't just sending tiny text packets here. We're talking about mission-critical applications, the European train control system, automatic train operation, and even remote driving. These require continuous, unbreakable service. Take onboard video surveillance, for instance. Pushing live video from a train blasting along at high speeds demands massive data rates, virtually zero latency, and absolute packet reliability. Any drop in service when a train switches cells or crosses a national border, yeah, that's just a non-starter. Unbreakable connectivity is literally an absolute requirement.
Which brings us right to Section 2, defining FRMC's multipath. This is the technological solution engineered specifically to meet those massive demands.
Let's break down this definition, because the wording really matters here. FRMCS Multipath is the coordination of at least two user equipments, or UEs, serving in parallel the same onboard application. I really want to emphasize that word, parallel. Instead of tying one application to a single modem, a single onboard application leverages multiple hardware connections concurrently. It's all about distributing that one application stream over multiple separate UEs at the exact same time to achieve that ultra-high reliability.
Let's trace how this actually flows. On the train, the FRMCS multipath function sits within the onboard system and branches out to multiple UEs. Those are your physical radio modules. Each of these UEs establishes its own completely separate transport path through the access and core networks. And then, those independent paths converge back together at the multipath function located over in the fixed infrastructure. This core principle means that even if one individual transport path completely drops out, the single data stream survives without a hitch.
Now, let's shift our focus to the actual network topology in Section 3, the multipath architecture. Let's see where these functions actually live. So the FRMCS multipath function is fundamentally a distributed system. It's split right down the middle into two main components. On the one hand, we have the multipath client. This lives right there on the train within the onboard system, and its whole job is managing those local radio modules. Then, on the other hand, you have the multipath gateway. This resides back in the fixed infrastructure. It's the brains of the operation when it comes to managing the routing and dictating the overall multipath policy for the entire network.
Now, to get these two separated components working in perfect harmony, they talk to each other across two specific reference points. You can think of this kind of like an OSI layer abstraction. First up is the FSMPM, which is strictly the control plane. This is where the client discovers the gateway, they swap info about available paths, and negotiate the rules. Then, we have the FSMPU. This is the user plane, where the actual data transport happens. And practically speaking, this is where we get into the really cool deployment of protocols like Multipath TCP, MPTCP, and Multipath QUIC, or MP-QUIC. These protocols are what actually allow the system to bind multiple IP addresses into a single, unbreakable logical connection across all those different paths.
So that raises a pretty fascinating question, right? Once the client and gateway have actually established all these multiple paths, how does the system actively manage, control, and optimize those concurrent data streams in real time?
Let's unpack that in Section 4, Data Flow Management. The multipath function comes back with some seriously dynamic real-time capabilities. First, it handles data path selection, meaning it's constantly evaluating policy to pick the best eligible paths. Then you have QoS control, ensuring those ultra-strict quality requirements we talked about are actually met. It can also execute data path switching, instantly moving a data flow to a new path if a connection starts acting up. But the real heavy hitters here are the last two, data path splitting and data path duplication. So the crucial point is understanding the difference between these two actions, because they serve very different purposes. Data path splitting takes the packets of a single data flow and distributes them across multiple paths. This is perfect for aggregating bandwidth, like when you need to push a really heavy video stream. Data path duplication, however, takes the exact same packets and copies them across multiple paths simultaneously. This is purely for seamless, bulletproof failover. If one network suddenly dies, the system doesn't even flinch or reconnect because the duplicate packet is already arriving via the second path. And those practical protocols we mentioned earlier, MP-QUIC and MPTCP, are absolutely vital here. They use packet sequence numbers to seamlessly stitch those split streams back together or just instantly toss out the redundant duplicated packets at the receiving end.
All right, let's move to our final topic, Section 5, Cross-Domain Transport.
And this brilliantly illustrates the sheer flexibility of the whole architecture. What we're looking at is a single onboard application, routing one data path straight through the dedicated FRMCS network, while simultaneously routing a second data path through a totally separate public mobile network operator, or MNO. The system is literally managing data flowing over a private rail network and a public cellular network at the exact same time. It's just wild.
So the FRMCS multipath function is built to be unbelievably adaptable. Yes, it uses the dedicated FRMCS transport domain, but it can smoothly push traffic onto non-FRMCS domains too. We're talking public MNOs, non-terrestrial radio access like satellites, local Wi-Fi or Wi-Fi networks, and even legacy 4G EPS networks. It basically grabs whatever connection is available to keep that link alive.
But here is the real magic of this entire setup. Application transparency. The mission-critical systems on the train, the brakes, the ATO, the video feeds, they are completely oblivious to this massive multi-network routing operation. The decision on whether to split packets over 5G and Wi-Fi or duplicate them over a satellite link is entirely hidden from the application stratum. The application just hands over its data and the multipath function makes sure it gets there. Period.
We've seen how FRMCS Multipath spins this incredibly resilient web of connectivity to power the next generation of digital rail. But as rail operations become fully autonomous, it definitely leaves us with a provocative thought. What new, totally uncharted transport domains will the multipath function need to conquer next to keep everything moving safely? Thanks, we can see in next video.